All right, everybody. Again, my apologies on the test mix-up. I would say, equally frustrated as you, so. In case rumors start swirling, obviously, like, third hour that's still today is going to be in the same boat as you, but my 6th-hour class should be able to take theirs tomorrow as planned. So don't get too spreading rumors about the test being canceled in case you're talking to a 6th-hour person. Okay, so I'll adjust the Power School calendar today before I leave, but you guys will, I'm sure, speak with other people before then, so just be careful about who you're saying what to. Okay, I appreciate that. All right, so we're moving on to the next chapter, and chapter 10 is about parametric and polar functions. So the first section we're going to talk about here is going to be about parametric functions. So a parametric function is not like a type of function in the way that we think about like an absolute value function or a logarithmic function. Rather, a parametric function is like a different way of writing a kind of function. So, for example, we write something like y equals x squared. Represents a function, right? Everybody's okay with that? The parametric version of this will define a way to pick or define a function that gives us our x coordinate, and we define a function that would give us our y coordinate using some dummy variable. We represent that, or that dummy variable is our parameter. So in this case, like t is our parameter. So this is like our y equals x squared is like a function representation of y equals x squared. And then the system that we wrote here is like our parametric version of the same function. So it's just a different way to represent the things that we've already been dealing with. So let's define this now formally. So if we take the graph of the ordered pairs, xy, where x is some function in t, and y is also some other function in t, So that set of ordered pairs is what we call a parametric curve. And we say that the two functions, f of t and g of t, are the parametric equations for that curve. And we say that the variable t is the parameter. And we say that the interval I is the parameter interval. So that's a lot of just vocab there, right? So you might ask, like, what was wrong with the way we were representing things before? Like y equals x squared or whatever? Why are we adding in this new way of kind of graphing things or representing functions? And the answer to that is, this allows us to create functions that would be kind of impossible to make using like the regular Cartesian coordinate system. And we'll use our calculator to generate some interesting examples here in a little bit. So let's do that. So let's say that we have the parametric function where x is defined by t squared plus 1 and y is defined by 2t. And we're going to graph this on 3 different intervals and take a look at what the graphs look like. And we're going to use our calculator to kind of do this. So I'll write down that information then, and I'm going to pull out my calculator here in a second. I'll give everybody a chance to write this example information down. While I get everything set up to get the calculator out, kind of show you what this is going to look like. If you have your calculator with you and would like to follow along, I'd invite you to do so. If you're more comfortable just kind of sitting and watching, that's cool too. Okay, we ready to kind of look at our calculator here? Okay, so the first thing I'm going to do is I need to change the mode of my calculator. So I'm going to press the mode button. So notice kind of in the middle of the screen here we have the options func, par, pol, and seq. So function, or func is short for function. That's the mode we're typically been using in all of your math classes up until this point. PAR is short for parametric. That's what we're going to be using today. POL is short for polar. We'll use that a little bit later this chapter. And SEQ is short for sequential. We don't do that in this class. Everybody okay there? Okay. So now that I've done this, if I go to the y equals menu, you notice that the y equals menu looks a little bit different, right? So for each function, you're given an x and a y spot where we have to give our function for x1 in terms of t and our function for y1 in terms of t. So in our example, x is t squared plus 1. So if I press the variable button, notice when I press it this time, it automatically gave me a t instead of an x. The calculator knows which mode I'm in, and because I'm in parametric mode, it's automatically giving me a t instead of an x there. Okay, I just press the regular old variable button where I usually get my x, and I'll do 2t. Is everybody okay with what we've done there? Okay. Good. So the next thing I need to go and do is go to the Windows button. So the last thing I need to do is just tell my calculator the interval for my parameter. So for my first example, my interval goes from -3 to +1. So my Tmin should be -3, and my Tmax should be +1. And I'm not going to mess around with that T-step, really probably ever. But I will change my x and y's because I was graphing something else in another class. And I'm just going to make the x and y's -10 to +10, like we would have in a standard window. Okay. Everybody okay there? So if I hit graph, let's take a look at what we got. So I get a graph that looks kind of like this. Ben? Whatever it was at, we're not going to change it. Some big kooky number. Some kooky looking decimal, right? 0.1 something, 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 something. Sounds good. We're not going to mess with it. As long as it's small, you should be fine. You get too small and it'll take forever to graph something. If you get too big, it's going to give you a crummy looking graph. So it just has to be something kind of smallish. Okay. What do you notice about looking at this graph right away? Does this pass a vertical line test? No, right? So with our standard like Cartesian definition of a function, this would not be one, right? However, notice that we created this just using functions, right? So it allows us more flexibility in dealing with things when we're in parametric, or by using a parametric system. It allows us to deal with these things that aren't functions in our traditional sense of the word, but we can still graph them, we can still work with them. It's much easier to kind of deal with. Everybody okay with that? What if I wanted to graph this on the interval instead from -1 to +2? How would I change things there? So to graph this under a different interval, I go back to the window, and I'm going to change the Tmin and Tmax. So in this case, what should the t min be? -1, because my interval goes from -1, and the t max should be +2, because my interval stops at 2. And then I'll hit graph again and take a look at what I get. A little bit different, right? Still not a function in the Cartesian sense, but perfectly acceptable as a function in the parametric sense. Everybody's okay with that? Okay. And then our last example goes from -2 to 3. So we'll go back and change and take a look at what the graph looks like this time. Okay. Is everybody okay there? Just kind of playing around with how to use our calculator to graph something in parametric mode. Let's look at a second example. Let's this time graph the parametric equation from, or where x is equal to sine t and y is equal to cosine t. What other piece of information haven't I given you yet? I haven't given you the interval over which to graph this, right? However, and even though I haven't given this to you, we can probably make a feasible guess as to what that interval might be to get a good complete picture here. What would, if you were to venture a guess as to what interval you'd want to use here, what would you guess? So the interval is going to be the values of t that we need to consider, right? What function is operating on t? Sine and cosine, right? What do I know about sine and cosine? We know a lot, right? We spent an entire semester talking about trigonometry, so we should feel very comfortable about dealing with sine and cosine. So if I were to pick values for t that would give me a representative picture using sine and cosine, what values of t might we be interested in? Somebody just take a guess, and we can talk about whether it's a good guess or a bad guess, but just take a risk. It's not a big deal. -1 to +1, okay? So if I take sine of -1, and I take all the values up to sine of +1, are we going to get all the possible outputs from sine with that? No, right? Think about what the graph of sine looks like. Does the graph of sine change all the time, or does it repeat itself? Repeats itself, okay? How long does it take for, along the x-axis, for sine to repeat itself? In other words, I'm asking, what's the period for sine? 2 pi is correct. So stands to reason that a good length for my interval here would be 2 pi units, right? So what interval might I pick then that has a length of 2 pi units? How about 0 to 2 pi? That sounds excellent. Now, for this to come out right, what other thing do I have to check on my calculator, though? I have to check the mode of my calculator to make sure I'm in radian mode. Now, most of us are probably in degree mode, given the most recent chapter we've been working on. And I would suggest to you, after we finish today, after we turn our calculator into radian mode before you leave class today, turn it back to degree mode into function mode, so when you try to take your test the day after tomorrow, you're not like, why is my calculator not doing anything correctly? Because it's probably that. Okay. So we do that. Let's change our interval then from 0 to 2 pi. And we'll hit graph. But before we hit graph, what do we suppose this picture is going to look like? Anybody with an idea here? Because we already technically know the answer to this. Wait, it's what? Specifically what circle? The unit circle, yeah. So if we hit, oops. So if I go and I change this to sine of t, and then cosine of t, I get exactly the unit circle. Is everybody okay with that? Okay. Does everybody feel reasonably comfortable taking a parametric equation, getting a graph out of it with our calculator? We feel okay about the vocabulary involved when we talk about parameters and intervals and all this? Okay. So let's next look at how we convert from parametric form to Cartesian form. So let's say we have the parametric equation. X is equal to 2 minus 3t, and y is equal to 1 minus t, where t is on the interval from negative infinity to positive infinity. So how many variables do I have in this parametric equation? I have 3, right? I have x, I have y, and I have t. Does everybody agree with that? Okay. If I want to convert this back into a Cartesian equation, how many variables should be in that equation? 2, x and y. Everybody okay with that idea? So to convert from parametric to Cartesian, what I really need to do is eliminate the variable t. Everybody's okay with that idea? This shouldn't be too bad, considering that t is a parameter or a variable in each of my 2 equations. All I need to do is take one equation, solve it equal for t, and then substitute it into the other equation and do some rearranging. Everybody okay with that idea? So if I look at my 2 equations, x equals and y equals, which one of them would be a little bit more convenient to get the t by itself? The y, right? Why is that equation going to make life a little bit more convenient? No fraction will be involved, right? So to solve for t, maybe I add t to the other side and subtract y to the other side. That gives me this. I can then substitute that into my other equation. Oops. And I clean things up a little bit and I get this. Is that the form that we usually represent a function in Cartesian land? Is that the way we usually write our functions? X equals yada, yada, yada? No, right? Which variable usually comes first? We usually want the y by itself. So that's easy enough to do. I'll just rearrange things a little bit. I'll add 1 to both sides and then divide both sides by 3. So my Cartesian form would be y equals 1/3 x plus 1/3. So what would I expect the graph of this to look like? A line, right? Whose slope is 1/3 and whose y-intercept is 1/3? Let's just confirm that quickly. Sound good? Okay. So I'll go back, and for x, I'm going to do 2 minus 3t. And then I'll have 1 minus t. And my t step, I can't do negative infinity, so I'm just going to do, I'm just going to pick a very large number, so I'll just do -1 times 10 to the 99. And then I'll do +1 times 10 to the 99. And I'll just use that as a substitute for positive or negative infinity because, I mean, as far as our calculator is concerned, that's good enough. Everybody's okay there? Oh boy, it said that was too big. Well, that's unfortunate. How about I just do that? Is that okay? Or is it still going to yell at me? Okay. Oh, I bet I know why. I bet that this can't exceed that. There. Good enough. Anyways, there we go. Looks just like what we expected, right? A line that's not very steep. Its slope is 1/3. It passes through the y-axis at about 1/3, exactly as we'd expect. Okay? Everybody's okay with what we just did there? Okay. What would also be nice is to be able to determine the domain and range for our function in Cartesian form. This is relatively easy to do because we can use our parametric form and our interval, or our parameter interval, to determine that. So if I take the 2 endpoints of my interval and I plug them into x, that's going to give me my domain. If I plug negative infinity into that, what am I going to get? I would get this, right? Now, this isn't really mathematically correct what I'm doing, but it's going to give us enough intuition to tell us what's going on. Everybody's okay. You can't really plug infinities in for x, but we'll do it anyways because it gives us the right idea. So negative times negative times negative is positive, right? And what's 3 times infinity? Still infinity. And what's 2 plus infinity? Still infinity. So we're going to have positive infinity will be the endpoint of our domain, right? Everybody's okay with that idea? If I do the same thing then, but instead use the positive infinity and plug that in, I get negative infinity. So I can see that my domain is negative infinity to positive infinity, right? Everybody's okay there? How else could I have done that? Is there an easier way for me to have thought about this? Another way I could think about this is if I just think about the function x equals 2 minus 3t. T is like the independent variable, and x is like the dependent variable, right? So in Cartesian land, t is like my x, and x is like my y, right? Here we're told the domain for this function is negative infinity to positive infinity because the parameter interval is that. So if I look at my function here, x equals 2 minus 3t, that's a linear function, right? If the domain for a linear function is all real numbers, what's the range also going to have to be? All real numbers. So I don't even have to play this plug the infinities in game. Is that okay? Now, it's certainly fine to do that. You don't have to think about it that way. But if I apply that same logic to the y-coordinate, what's the range here going to be? Also negative infinity to positive infinity, right? Since if I look at y equals 1 minus t, that's another linear function whose domain is all real numbers, so the range would also have to be all real numbers. Everybody's okay with that idea? Should we do it again? Yeah? So let's look at another example. All right. So first thing I want to do is try to eliminate t. Which one of these two equations would be easier to solve for t? X equals or y equals? Hopefully you'd choose the x equals. Why would we choose that one to be easier? There's no squared in it, right? We wouldn't have to solve a quadratic, which is preferable. So when I solve for t, I get that t is equal to negative x over 4. Everybody's good with that? So if I substitute that now into the y equals equation, I get 2 times negative x over 4 squared plus 1. How do I square a fraction? Well, I square the numerator and then I square the denominator. And then how do I multiply two fractions? Multiply the tops together and the bottoms together. So that gives me 2x squared over 16 And when I reduce that, I end up with x squared over 8 plus 1. What kind of function is this in the Cartesian sense? It's quadratic, right? What should the shape of the graph look like? Has a special name. Parabola. Yep. Let's just confirm that by graphing the parametric form and seeing if it matches. Let's fix our window, or our interval, I guess I should say. Looks like a parabola to me. What do you guys think? So that's good. What's the domain and range for this going to be? Well, for the domain, we're going to use the x equation. Bless you. And I'm going to start by plugging in my values from my interval. So my domain should be negative 16 to positive 8. Is everybody okay with how I did that? Remember, when we write our interval, it always goes small to big. So the smaller number always comes first, and the larger number always comes second. So to do our range, we're going to use the y equation. And we're going to do the same thing. We're going to start by plugging in the boundaries for t. Let's see, that's 17. And then if I take t equals 4, well, negative 2 squared is, 9, yes. Sure. Thank you. And that is 16 times 2, 33, right? Everybody's okay here? Is this right? So would I write this? Is that correct? It's actually not. Why did this work so nicely for the domain and not for the range? Look at the kind of function I'm dealing with in the domain. What kind of function is this? This is linear, right? That means it's always either getting bigger or getting smaller. So the boundaries at the end of that interval are going to be exactly what I need, right? Look at the equation for the range. What kind of an equation is the range? Quadratic, right? That means that like the high and low points aren't necessarily going to be the ends of the interval, right? The low point occurs at the vertex of the parabola. Everybody okay with that idea? So I actually don't want to use t equals -2. That's not going to be the lowest point on my parabola. What is the vertex? What value of t gives me the vertex for y equals 2t squared plus 1? Should be able to look at that and just be able to tell me. Anybody want to venture a guess? Just take a risk. 0 is correct. So if I do that, I get y equals 1. That should be the value there. So for those of you that weren't sure how Kara got that value for t, if we remember for the quadratic function y equals ax squared plus bx plus c, the vertex, the x coordinate is -b over 2a. So if I go back and I look here, what is the value for b? 0. So 0 over 2a is going to be 0. So that's how Kara knew that the x coordinate for the vertex should be 0. Or I guess in this case, the t coordinate, since we have y equals 2t squared plus 1. So we do have to be a little bit careful when we're finding the domain and range. While the endpoints of our interval for the parameter are going to matter, they're not necessarily just plug and chug. We also have to think about the function that we have involved for the x or y coordinate. Everybody okay with that idea? Let's do another. So what are we going to do here if I want to try to convert this into Cartesian form? How am I going to eliminate a t from this? Is it possible to do that algebraically the same way we've been doing it before? No, right? So we're going to have to be a little bit sneaky on this. So before we get sneaky, let's type this into our calculator to kind of see what we're going to get here. I hate you so much. Okay, so I'll type that in there. And then we're going 0 to 2 pi. Let's hit graph. So what is this equation, or what is the shape of this graph? It's a circle, right? Okay. Does anybody remember the equation for a circle from their geometry course? I know that was a long time ago. No? So x minus h squared plus y minus k squared is equal to r squared. What is h comma k? That's the center of our circle, and r is the radius. Okay. So if I look at this circle in our graph, what's the center for my circle? That's 0, 0, right? So I'd have x minus 0 squared plus y minus 0 squared equals some stuff, right? Everybody's okay there? So that simplifies down to just x squared plus y squared. Everybody's okay there? Okay. And then what is y? Or I'm sorry, what is x? Well, that's 3 cosine t. And y is 3 sine t. What is 3 cosine t squared? That gives me 9 cosine squared t. And what is 3 sine t squared? It's 9 sine squared t. And if I factor a 9 off, I'm left with 9 times cosine squared t plus sine squared t. Does anybody recognize something here? Yeah, very good, Bridge. Cosine squared plus sine squared is 1. So we're left then with x squared plus y squared is equal to 9. Okay. Let's look at going from Cartesian to parametric. I'll just start with an easy one. Let's say we have the equation y equals 3x minus 2. You want to do this the hard way or the easy way? I would pick the easy way also. How many times does x occur? Just once, right? There's just one time I have an x variable in there. So I'm just going to say x is going to be t. If I do that, what's y have to be? 3t minus 2. It's that easy. If the x occurs just one time, you don't have to do anything sneaky. Now, the only thing that's left is writing my interval. The nice part about doing it this way is because x is equal to t, whatever my domain is going to be the same as my interval. So what's the domain for y equals 3x minus 2? It's all real numbers. So that's going to be the same as my interval for my parameter, and I'm done. Yeah. So this is a polynomial, right? The domain for any polynomial is all real numbers. And since x and t are the same thing, the domain for my function is going to be the same as the parameter interval. So I just use that. You're welcome. That was an old Algebra 2 fact that we applied there. And I think we're close to out of time, right? Okay. So we'll finish up this section next time. Do you want me to list